Hi, so this video is devoted to the next topic, which is prisoner's dilemma and methods of ensuring cooperation in prisoner's dilemma game. So first we have to start with definition. So every prisoner's dilemma is characterized by the following structure. So two players have to make decisions simultaneously, which means under strategic uncertainty, having no information about decision made by the other player, and they have two available strategies, which are defect and cooperate. Of course, these strategies can be different, but the main idea is to ensure that two players can either cooperate, communicate and try to maximize the common payoff. Yeah, something like this. And the other option is not to cooperate, so try to pursue own self-interest. Own interest, yeah. Okay, so if both of them defect, each gets C. If both of them cooperate, each gets B. The best possible outcome if as player 1 decide to defect, getting A, and the second player decides to cooperate, this also corresponds to the worst possible payoff for the second player, which is D. And yeah, more or less the following structure of payoffs should be maintained. We treat this as a sufficient condition for this game. Okay, so when it comes to necessary conditions, you can easily detect that for each of the players, the dominant strategy is to defect. Let's analyze it from the perspective of the first player. If the second player decides to defect, then for me, C is better than D, I would defect. If the second player decides to cooperate, then for me, A is better than B, I will defect. So again, this is by definition of the dominant strategy, the strategy which is superior regardless of the decision made by the other player, of the strategy chosen by the other player. So we will have Nash equilibrium when both players decide to defect, and both of them have a dominant strategy to defect. And please keep in mind that in this case, Nash equilibrium, the outcome of this game, is not Pareto efficient. By definition, Pareto efficiency means that neither of the players can be made better off without making other player or players worse off. So in this case, if we analyze Nash equilibrium, it's possible to improve the payoffs of both players simultaneously. If we shift from defect outcome to cooperate outcome. Okay, so Nash equilibrium in this game is not Pareto efficient. And theoretically, if two players are rational, they should never ever cooperate. However, in real life, players still do. They cooperate. So there are several reasons. The most obvious one is that we are not perfectly rational players. We have some kind of moral sentiment, other considerations. So it's very similar to the dictator game we discussed during the classes, Even though theoretically you should accept any offer above 0, you do not, because of human dignity, I don't know, because your feelings were hurt or anything like this. So the same applies here. Even though it's perfectly, rational move to defect, regardless of what the second player decides to do, in real life, people still cooperate, because we are human beings, not perfectly rational players. Other solutions are iteration of the game. So if the game is played several times, then there are higher chances for cooperation. And this is what we are gonna discuss in a minute. and payoffs might be modified. Like we introduce some additional penalties or rewards to this game, then basically the structure of the game will change. We will not deal with prisoner's dilemma anymore, and there is some chance for achieving the cooperative solution. So to ensure that Pareto efficient outcome coincides with Nash equilibrium of the game. Okay, so when it comes to iterated prisoner's dilemma game, so the class of contingent strategies includes all the strategies, which can be adapted, adjusted, modified, based on the behavior of other player or players. So 3 common types are trigger strategy, grim trigger strategy, and tit for tat strategy. So the idea behind the trigger strategy is that players can penalize for defection. For instance, if you defect, I will not cooperate with you for 1, 2, 3, or any number of periods of your choice. And of course, both players have to be aware of this. Grim trigger strategy is a very radical form of the trigger strategy, and basically it means if you defect, I will never ever cooperate with you again. So if you defect even once, it means that I will never ever cooperate. And finally, tit for tat means mirroring the last move of the other player. Like for instance, if you cooperated in the previous round, I will cooperate with you during current round. If you defected in the previous round, I will also defect in this round, So this is the idea. Okay, so when it comes to finite iteration, there is a kind of a paradox, especially when you try to solve it using the method of the backward induction. So please consider this game. Like you can easily identify that both players have a dominant strategy to defect. So we deal with the classical prisoner's dilemma. Also, the structure of the payoffs coincides with the structure of payoffs in prisoner's dilemma. So assume that 2 players made an agreement to cooperate. So we start here in cooperate, and 324 for both players are the payoffs corresponding to this combination of strategies. Assume that each player cooperates as long as the other player does the same. So we play the trigger strategy, green trigger strategy to be more specific. Assume that this game is gonna last for... Okay, actually there should be 3 periods. Sorry for this. So assume that the game is gonna last for 3 periods, and please try to solving using the method of backward induction. So I will tell you in advance, if you decide to draw the tree, it's not gonna be particularly helpful in this case. So instead, please just try to analyze the logic of each player starting from the last round. And keep in mind that the only reason, for cooperating in this round is the opportunity to cooperate in the next round. So for instance, if I know that... So for instance, if we agree to cooperate, then I can defect and get 360 instead of 324. And the only reason for me not to do this, is to get an opportunity to receive 324 instead of 288 in the next period. So if you'd like to practice, please put this video on hold and I will just proceed with this. Okay, so technically speaking, finite iteration makes no sense if you try to solve this game using backward induction method. So I know that in the 3rd period there will be no future. So this game will end after 3 periods. So in the third period, it makes no sense for me to cooperate, because as I said before, the only reason to cooperate in period T is to, get a higher payoff in period T plus 1. So for instance, I want to cooperate with you in period 1 because I expect cooperation in period 2. So then in period 2, thanks to cooperation, I will get 324 instead of 288. Otherwise, if I expect that there will be no future of this game, so this game will finish in this period, then again it simply makes no sense for me to cooperate. Then I will just defect, and I keep in mind that you're gonna do just the same. So in the third period, it makes no sense to cooperate, and two players will inevitably decide to defect. Then, both players keep in mind that it makes no sense to cooperate in the second period as well. Because if in the third period both players will inevitably defect, then it makes no sense to cooperate in the second period, due to the same reason, because I can cooperate only for the sake of future cooperation. If there will be no future or no cooperation in the future, then it makes no sense for me to cooperate in this round. So in the second period, both players will decide to defect as well. So in this first period, the same logic applies. So both players keep in mind that there is no future after third period. Both players will defect in the third period. Keeping this in mind, both players will defect in the second period. So why to cooperate in the first period? Anyway, there will be no cooperation. So again, if you try to solve this game using the method of backward induction, you will see that cooperation makes no sense. However, we are gonna do something different. So let us start with assuming infinite iteration based on the Cournot model example. Okay, so as usual, this is market demand. Quantity demanded is equal to 100 minus P. Market is cleared, so quantity demanded is equal to the quantity supplied by two firms, and the quantity supplied by two firms is equal to the sum of quantities supplied by each firm. C1, marginal cost of the first firm, is equal to C2, marginal cost of the second firm. They are both constant and they are equal to 10. Okay, so first let us start with defining the outcome when two firms do not cooperate. So let's assume both of them defect, so they pursue their best strategies, and when they do this simultaneously, Nash equilibrium serves as the appropriate solution concept. So let us start with calculating firm's profit, payoff, under the Nash equilibrium. Again, if you'd like to practice in continuous strategies and solve it on your own, please put this video on hold and I will proceed with the solution. And here it is. So first we define profit of the first firm, profit of the second firm. According to first order condition, you have to calculate the derivative, first derivative, and equalize it to 0. So here you have two best response functions of the first and the second firms respectively. So then you have to solve the system of equations. You will see that the firms will produce the same quantity, which makes sense because they have symmetrical marginal costs. And in this case, their profits will be equal to 900. So if two firms decide to defect or to compete, then both of them will get 900. So now we will analyze the payoffs corresponding to decision to cooperate. So, So we will try to figure out what will be the profit for each firm if both of them decide to cooperate. So effectively it would imply that two firms act like a monopoly. So in this case, like based on the market demand function, you have to maximize profits of the monopoly. So here is the function for profit. According to first order maximization condition, first derivative has to be equal to 0. And when maximizing profits, monopoly will produce 45 units. So the corresponding level of profit is 2025. And if we assume that two firms will split this profit equally, which makes sense, taking into account that they have symmetrical costs. Each firm will get 1012.5 units of profit. Probably dollars, but for some reason I did not specify the units here. Okay, so if two firms decide to cooperate, then each firm will get 1012.5. We are done here. So now we have to calculate the profits when one firm decides to cooperate and the other one decides to defect. So let's say the two firms made an agreement to cooperate. So we start at this cell and assume that the second firm decided to stick to this commitment and produce one half of monopolistic output. So if two firms produce 45 units, then one firm would produce 22.5. So we assume that the second firm is a fair player, so it sticks to its commitment. And now we have to analyze how many units should the first firm produce in order to maximize its profit, keeping in mind that the second firm will produce 22.5 units. So here in the profit function for the first firm, you have to replace Q2 with 22.5. Then again, first order condition and optimal quantity, like profit maximizing quantity of output for the first firm is 33.75. So if you calculate profit of the first firm, you will get approximately 1039. And in these circumstances, if the second profit decides to cooperate while the first firm decides to defect, producing this quantity, the profit of the second firm will be approximately 759. So if the first firm decides to defect and the second firm decides to cooperate, then the first firm will get 1139 and the second firm will get 759. And analogously, if the first firm decides to cooperate and the second firm decides to defect, then first firm gets 759 and the second firm gets 1139. So as a result, you have a classical prisoner's dilemma. So in this case, both firms have a dominant strategy to defect, even though the corresponding Nash equilibrium 900-900 is not Pareto efficient. So Pareto efficient outcome is here when both firms decide to cooperate. Okay, so the question is whether it makes sense to sustain cooperation if the game is iterated every year or every quarter or every week. So let's say every period. So we assume that both firms are rational players and they both keep in mind that they can be better off under Pareto efficient outcome, cooperate. So assume that they agreed to cooperate instead of competing. So now we start at the point when both firms receive 1012.5 as a payoff. Okay, so basically this means that one period gain from cooperation is equal to 112.5. So thanks to cooperation, they both can get 1012.5 instead of 900. So as I said, 1 period reward for cooperation is equal to 112.5. However, if we agree to cooperate, okay, so if two firms agree to cooperate, then the first firm will always have a temptation to defect. So basically, if we are in this cell and the second firm decides to change the strategy, and compete instead of cooperation, then basically we move from this cell to this cell. So in this case, 1 period gain for defect is 1139 minus 1012.5. So basically it's 126.5. And let us also assume that both players play green trigger strategy. So let's say once one player defects, there will be no cooperation till the end of the world for the second player, and then accordingly it will make no sense to cooperate for the first player as well. So in simple words and in short, once any player decides to defect, cooperation makes no sense and there will be no cooperation. So we can say by defecting, the firm gets 126.5 profit, like let's say extra reward or something like that per 1 period. But then this firm will lose 112.5 per period forever, like each period till the end of the world. Okay, more details here. Okay. So, let's say the first firm decides to defect. If the first firm defects, then it will gain 126.5 per 1 period. And since, this is like one-time reward, and it happens in 0 period, like right now, we do not have to discount, and we just say that 126.5 is the present value of the gain. Why 126.5 is because if we start at this point when two firms cooperate and then the first firm defects, the first firm will get 1139 instead of 1012.5. So the effective reward is 1026.5. However, since we assume a green trigger strategy, it also means that starting from the next period and then each period till the end of the world, I will get, like at the first firm, I will get only 900 instead of 1012.5. So previously we cooperated, then I defected in 0 period. So from now on till the end of the world, this is the outcome. Like I know that the second player will never ever cooperate with me again. So as the rational player, I also defect. So we end up here and we stuck here. Okay, so 126.5 is the present value of reward. We do not discount because, it occurs here now at the current period. And we have to calculate present value of the loss. So if we know that the game is played infinitely and green trigger strategy is a thing, so we will have the same outcome again and again for every period, then you can apply the formula for calculating perpetuity. So I will get back to this in a minute, but basically if some payment if some payment occurs regularly, like once in a period, and there is infinitely big number of these periods, then the present value of all these payments, like aggregate present value, is equal to payment multiplied by 1 over r. So sigma is calculated as 1 over r in case of perpetuity, So it will depend on the number of periods assumed in this game, and we call it a discount factor. So the idea is like this. If you want to sustain cooperation, then present value of loss should, like, let's say if you want to make the players at least indifferent between cooperating and defecting, then present value of loss should be bigger or equal to the present value of gain. So again, this is 1 period gain associated with defecting, but then you will lose this 112.5 each period forever. So present value of loss should exceed or be equal to the present value of gain, and if you calculate this, you will see that the critical value of the real interest rate is 89%. So if interest rate is higher, then cooperation makes no sense, and there are no chances to sustain cooperative outcome. Okay. So in this case, we assume that the game is played infinitely. So we must sum up all the present values of loss associated with each period. So for instance, this will be present value of loss in period 1, present value of loss in period 2, present value of loss in period 3, present value of loss in period n, when n is infinitely big number. So if you sum up everything, then you will get 112.5 divided by r. Just following the mathematical properties of this series. Okay. So we can also assume that the total number of periods is equal to 2. So we have period 0 for now and period 1, which is the next period. So in this case, discount factor sigma is not 1 over r, but instead 1 over 1 plus r. Because in this case, we do not analyze perpetuity. We just have to discount solely for the next period. Keeping the same assumption, that we want to make players indifferent between defecting and cooperating. So present value of loss should exceed or be equal to the present value of gain. So when you solve this, you will see that the maximum value of the real interest rate is 11%. So if it's higher, cooperation will make no sense. And yes, it's fine to have a negative real interest rate. We can also assume that there is no perfect certainty about the number of periods, during which the game is going to be played. So in this case, we have to introduce R, which stands for the effective rate of return. I mean big R, capital R. And P will stand for the probability that the game is gonna last for the next period. So this is discount factor with effective rate of return, and it has to be equal to sigma multiplied by p, because obviously the maximum possible value for probability is 1. So in this case, if probability is equal to 1, so we have perfect certainty that the game is gonna be played for the next period as well, then there will be no difference between capital R, effective rate of return, and R, interest rate. So in order to define the effective rate of return, you have to use this formula, because again, this is just an effective discount factor with effective rate of return. So you will get capital R equal to 1 minus P sigma divided by P sigma. Here you have an example. So assume that total number of periods is 2. The real interest rate value is 10% per period, and there is only 50% probability that the game is gonna last for the next period. So 50% probability is assigned to the outcome when we play this game for 2 periods, and 50% probability is assigned to the outcome if that we played this game only for 1 period. Okay, so in our case, the value of sigma is calculated as 1 over 1 plus r, because we have only 1 period to discount for. So using this formula, the value of sigma is approximately equal to 0.91. So again, you have all the values known, you put them to the formula, and you will get the value of the effective rate of return of 1.2. So the effective discount rate or effective rate of return is equal to 120%. Okay, so speaking more generally, so assume that we are gonna play this game for the unknown number of periods. So we analyze the effective rate of return and assume that both players play green trigger strategy. So there is no cooperation after a single case of defection. Okay, so we start as usual here, cooperate, and 1 period gain from defection is equal to A minus B. So if the first player betrays the second player, then the first player will get A instead of B, and 1 period gain is calculated as A minus B. However, then for each period, so this outcome will be unachievable. So then for every period, both players will end up here, defect. So 1 period loss will be equal to B minus C. So each period I will get C, however I could get B. So present value of gain is equal to A minus B, because this is 1 period gain, 1 time gain, which happens here and now. And present value of loss will be calculated as B minus C, 1 period loss divided by 1 plus R. So in this case, in order to prevent defection, present value of loss should exceed the present value of gain, and you will find out that the value of effective rate of return should be smaller than B minus C divided by A minus B minus 1. So under this condition, cooperative outcome will be sustained. So additional example, if we know that both players play not green trigger strategy but tit for tat strategy, then it will look a bit differently. So 1 period gain remains the same, so this is A minus B. However, in case of 1 period loss, we have B minus D. I will explain why. So if we assume that both players play tit for tat strategy, and again for the sake of simplicity, let's assume that the first player decided to defect. So in period 0, we move from this cell to this cell. So then player 1 will get A instead of B, and 1 period gain will be calculated as A minus B. However, in order to, get back to cooperative outcome, the first player will have to sacrifice payoff in period 1. I mean, in the next period after period 0. So we move from this cell, defect, cooperate, to this cell, cooperate, defect. So the second player will mirror the strategy of the first player in 0 period. So in 0 period, the first player decided to defect, so the second player will decide to defect in period 1. And in order to restore cooperation, the first player will have to cooperate in the first period, even though, it will imply some losses. Because in this case, the second player will defect in the first period. So again, we start with cooperate, then defect, cooperate, and then cooperate, defect, just for the sake of restoring the trust of the second player. So in this case, loss will be B minus D. Okay, so present value of gain is the same, A minus B, and present value of loss will occur in the next period. That's why we have to discount. So it will be B minus D divided by 1 plus R. So in order to prevent defection, R shall be smaller than B minus D divided by A minus B minus 1. Okay, I hope it's fine. So iteration is one of the methods to sustain cooperation in prisoner's dilemma, and penalties and rewards is another method. So again, here we have a classical prisoner's dilemma when both players have a dominant strategy to defect. But let's say that we introduce some penalty for defection. So each party which decides to defect will lose 15 units of something, 15 units of utility, let's say. So then, instead of 5, 5, we have minus 10, minus 10. Instead of 120, we have 20 minus 15 for defecting party, analogously here. And yeah. So in this case, if you try to define Nash equilibrium using best response analysis, you will see that now cooperate is the equilibrium outcome of this game. So this is Nash equilibrium now. Like formally, this game is not a prisoner's dilemma anymore. So basically, you can say that introducing penalties and rewards implies changing the structure of the game. So it's not a prisoner's dilemma anymore, with defect as a dominant strategy, but just some other type of game in which Pareto efficient outcome coincides with Nash equilibrium. Analogously, you can introduce reward for cooperation. So then cooperating party will get additional 15 units of utility or something. So then instead of 120, we have 1620, analogously 2016, and 2525 for cooperate outcome. So again, now cooperative outcome is a Nash equilibrium. So we see a coincidence of Pareto efficient outcome and equilibrium outcome of the game. And finally, like the last method to promote cooperation is leadership. So in this game, assume that there is some disease, which is funny, especially take into account all the circumstances. So there is some disease, and two countries, Poland and the United States, have to decide on whether invest in research or not to invest in research simultaneously. So if you try to solve this game, you will see that this is a classical prisoner's dilemma, where no research is a dominant strategy for both players. So we will end up here, and yeah, something like that. However, you have to keep in mind that US economy is of the bigger size than Poland. So if there is no vaccine for this disease, then more people will die in the United States than in Poland. So subsequently, the costs will be higher. The costs associated with having no vaccine will be higher for United States than for Poland. So if you try to change the structure of this game accordingly, you will end up with something like this. And if you solve this, you will see that for Poland, no research is an optimal strategy, and for the United States, research is an optimal strategy. Okay, probably I did not mention this before, but the idea behind the research is that when something is invented, everyone can use it. So United States cannot invent vaccine only for United States citizens. So once it's developed, then Poland will have an opportunity to use it as well. Okay, so that was it, and thank you for watching.